All right, we're going to get going. Good afternoon. My name is Philippe Gobel. I'm the head of the Aerospace Engineering Department here at Illinois, and it's really my pleasure to welcome you to this Stillwell Memorial Lecture. This lecture series was created in honor of Professor Shel Stillwell, who 70 years ago, and at the age of 27, founded our department. For reasons that I cannot fathom, he remained department head for 32 years. This lecture series gives us the chance to bring to this campus distinguished speakers in the field of aerospace engineering and science, and who can do this better than the chief technologist for NASA, whose official job description is, and I quote, to serve as NASA's administrator's principal advisor and advocate on matters concerning agency-wide technology policy and programs. In his position at NASA, which he joined about a year ago, Dr. Miller has the opportunity to have an impact in many different fields. He even had an impact on our department since his former student, Professor Soonjo Chung, is now part of the faculty here. So it would therefore make sense for Soonjo to introduce today's speaker. So, Soonjo, it's all yours.
Right, so hello everyone. I'm so excited to have the opportunity to introduce my former PhD advisor and great teacher for myself, Dr. David Miller, NASA Chief Technologist, and he's a Jerome Hunsaker Professor of Aeronautics and Astronautics at MIT. He has worked on many broad range of NASA missions, NASA programs, ranging from International Space Station, Space Shuttle, and James Webb Space Telescope. That's a 6.5 meter segmented meter telescope that's going to be launched soon, hopefully. And he was a principal investigator of various missions, including MEDEC active control experiment that was flown on Space Shuttle and International Space Station that investigate the important control structure interaction issues. He was recently principal investigator of X-ray regolith X-ray imaging spectrometer for OSIRIS-REx. That's the asteroid sample return mission. He was principal investigator of that, and he was involved in NASA CubeSat launch initiative. I learned a lot from Dave, but there are two things I want to share with you that really impacted my career at Illinois. The first thing is that how caring, supportive, and wonderful he is as a mentor and teacher to his students. Second thing is that his research philosophy of bridging the gap between theory and practice, not only in graduate student education and research mentoring, but also in engineering education. So one prime example is he has initiated and successfully developed this CDIO, MIT's famed conceive, design, implement, and operate hands-on education initiatives where students are exposed to real-world applications and end-to-end process of space product development. So one successful product out of this multi-semester sequence projects was Spears microsatellites. I believe many of you watched this video of these soccer ball size satellites floating, actually precisely speaking, flying information and interacting with the astronauts. So that was the for testing and validating some of the advanced formation flying control algorithms. So in my opinion, that was the most successful space flight projects and development initiated and developed by undergraduate students and also in academic institutions. He was recently vice chair of Air Force Scientific Advisory Board, and he got his undergraduate degree and PhD, actually Doctor of Science degrees from MIT. And since 1997, he was a faculty member at MIT. So he's currently NASA Chief Technologist. So it's my great pleasure to welcome Dr. Miller as this year's Stillwell lecturer. Thank you.
Well, thank you for that wonderful introduction. If you want to hear stories about Professor Chung at his graduate program, you have to join us at the reception. I'm happy to share many stories, but tremendous graduate student. And I think I think the faculty in the room realize that the most important people you work with in a university are the students. And so a lot of your career is owed to them, and I owe a lot to Soonjo for how he's helped advance my career. So today I'd like to tell you about technology at NASA. I'm sort of going to do a little bit of a wandering path through this. I'll give you an overview of what I do. I'll give you an overview of what the different directorates are in NASA and what they do, and then talk about some of our big missions and try to point you to ways that you can get involved in the process. So I'm going to excite you with an org chart. That's always a good way to start. I'll show you where I am in this, but some of you may not be that familiar with NASA, so I'll try to show you sort of the high level how it works. Our administrator is Mr. Charles Bolden. We currently are trying to fill the deputy administrator position. That's happening as we speak. And the associate administrator is Mr. Robert Lightfoot. The administrator and deputy are political appointments, and the associate is the highest government service person in the agency. The chief scientists and the chief technologists are advisors to the leadership of NASA, and we're actually, I think it's very insightful for NASA to bring the people that fulfill that position in from the outside world, outside of NASA, to bring a set of fresh ideas to NASA. And these are positions that rotate roughly every 2 years. So while I've only been there for about a year, I'm only a year away from retirement, so that's starting to make me sad. But the other thing is there are 10 directorates. You're probably familiar with a lot of these. JPL is different from the rest in the sense it's an FFRDC, a federally funded research and development corporation, and all the rest of the centers are government labs, and they serve different roles. I guess a couple of centers that I was not familiar with coming in is Stennis Space Center, which is located in Mississippi. That's where they light off all the rockets, but they don't let go of it. So it's every engine that's been fired gets fired at Stennis first. So they give the seal of approval. And Armstrong is what we used to call the Dryden Flight Research Center. This is out at Edwards. It was recently renamed a little less than a year ago. And you're probably familiar with some of the others, but if you're not, you can ask me later. So I was going to start with what I do, and I'm still trying to figure out this job. It's challenging to come up with speed in such a big organization in such a short time. So there's sort of 6 things I do. So I provide guidance on policy direction for technology investments and prioritization, and we do that on a 4-year basis. We develop our roadmaps, which are kind of what we could do and work on in terms of technology at NASA. And then every 2 years, we work on what we call the STIP, which is the Strategic Technology Investment Plan, and that's what we should do, and then the budget always determines what we will do. So it's kind of a narrowing down to figuring out where we want to make our investments. I also work on analyzing our investments, seeing where we're making progress, seeing if we're doing duplication across the agency, across all the directorates, not only space, but also aeronautics. I engage with other agencies, so it's what they call sort of up and out. I look at the high-level picture, the long-range vision for technology investment, and try to coordinate that with industry, academia, and other government agencies, as well as with foreign partners. We also have a I was going to say an innovative office, but it's actually the Innovation Office, where we provide leadership for policy and strategy to run things like innovation prize competitions and agency grant challenges. So if you're familiar with some of our grant challenges, we have an asteroid grant challenge, we have different prizes, there's a whole bunch of these, and I'll talk about those in a moment. But it's really innovative ways to engage the broader community in our mission. Tech transfer runs out of my office, as well as commercialization activities across the agency. But the best job is serving as the advisor to the administrator, and probably the nicest realization that I've had is how much access I'm able to get with the leadership, and that's been wonderful. So let me step through those. I'll start with the technology areas. In our roadmaps, these are the 15 technology areas that we've identified, and underneath this, there's a whole bunch of detail. They are the 2014 roadmaps. It's now 2015, so they're coming up for public comment here any day. And so if you want to look through those, probably by the end of March, they ought to be available for public comment. If you want to look through that and say, well, you're missing this very important technology, maybe you ought to add that to the list, we'd be happy to hear those comments. When I look at a chart like this, I like to think, where do I plug in? For myself, I guess I would say robotics and autonomous systems. I'd say science instruments and observatories, modeling and simulation are kind of the areas I think I best plug in. But some of you probably see a different mapping here, and hopefully all of you see a place where you can contribute to NASA. On the other side, there's our innovation and grand challenges program. These are just a short list of a much longer list of different challenges we have out there. And actually, we found out that across the agency, these are all located at different sites. So we've made a one-stop shopping here at nasa.gov/solve. So if you're interested in participating in these things, and there are many more, feel free to take a look, put together a team in your, an extracurricular activity at Illinois here, and try to go for some of these. Some of these have cash prizes. Some are as large as $1 million. Some are, congratulations, but you have to look at the rules. An example here, and actually this sort of faded out image here is every time when we land at Mars, en route to Mars, we spin the spacecraft for gyro stabilization. But then when we enter the atmosphere, we want to have our center of pressure from the atmosphere and the center of mass of the vehicle be offset so we can actually get a little bit of lift and we can guide it through the atmosphere. But then we want it to be back in balance for when we come under canopy, under parachute, and land. So what we do is we throw off balance masses. These are tungsten slugs that are on the order of 75 to 150 kilograms. So we throw off 150 kilograms of this at the top of the atmosphere to get our CG and center of pressure out of balance, and then we throw off another 150 kilograms. So we recently, in order to get rebalanced just before we pop the chutes. And so there's 300 kilograms of mass that we're dropping off at Mars. So one of the challenges, it just closed, so sorry, we already have a winner, but just to give you a feel for the kind of challenges we have, is how would you use that rather than just sort of dead mass? How would you use that? We got a bunch of very innovative ideas on how one could use that kind of mass when it's, those masses are dropping through the Mars atmosphere as well. And there's a lot of interesting things you could do. So that gives you a sample of what these challenges are like. So now let me give you a tour through the agency. It's really one agency, many missions. So there are 4 directorates. There's the Human Exploration Directorate. There's the Science Directorate. And those 2 are really what we call our mission directorates. So they have a bunch of missions. You probably know a bunch of them. I'll go into some of them later. And then there's 2 more directorates. One is Space Technology, which really sort of feeds technology to these directorates. And there's also Aeronautics, which is also a technology mission directorate that feeds not only to these areas, but also to the commercial sector, the aviation industry, and so forth. And in fact, Space Technology, one of their customers is also the space sector, the space commercial sector. So you can think of these 2 as sort of our mission directorates, and these are sort of technology enabler directorates. So let me step through them one at a time. I'll start with Human Exploration and Operations Mission Directorate. It's the largest. It's roughly $8 billion a year in terms of funding. They operate a lot of things. They operate space station. They operate commercial crew and cargo. They're building the SLS rocket. And the ultimate mission right now, our horizon for humans, is to get to Mars. The way we're trying to do that is to learn how to do that in space station, which is what we call Earth Reliant. That's where we want to work out all the technology and the science to enable us to do long-duration space flight and survive in deep space. Then the next phase of that will be the proving ground, and this is where we're going to go out into deep space, sort of beyond to the lunar environment and beyond, and sort of the first venture out beyond the Earth-Moon system. And this is where we want to practice with our tools and make sure we understand how they work and make sure they're robust. And then eventually we'll go to Earth independent, where we'll actually make the mission to Mars. We're sort of looking at the 2030s as that time. You can sort of think about this as Mercury, Gemini, and Apollo from the Apollo era. Mercury, where we wanted to figure out if we could even live up there. Gemini is where we figured out if we could work up there, and then eventually Apollo is where we went to the destination. This is science, and I love this chart because it shows how much is happening in science. The way to read this is this upper panel is what we're doing on Earth science. And when you see all these satellites, these are either satellites that we have that we're designing, or we're building, or operating, or in extended mission right now. So this does not go back to the full history of Earth science that NASA has worked on, or NOAA have worked on. But it also includes missions where NASA is a partner with other agencies, because this is an arena where there's a lot of partnerships that go on with the Department of Defense, international partners, with NOAA, and so forth. This chart is about astrophysics. So you can see things like the James Webb Space Telescope, that's supposed to launch in 2018. The Chandra X-ray Telescope, which has been up for quite a while, almost a decade, I guess. Hubble is up here, and so forth. So this is astrophysics. This is planetary science. So these are all the missions out to the planets. In fact, there's an inset here showing all the things that we're doing around Mars. It's quite an active destination for us. You've probably noticed that Dawn has just arrived at Ceres, which is a dwarf planet. I guess if Jupiter weren't around, then that's where the asteroids in the asteroid belt would have aggregated into a planet. You've probably heard about Rosetta and the Philae lander on the comet late last year. We've got OSIRIS-REx. You mentioned that coming up here. I'm looking for New Horizons. So we're going to visit Pluto here in I think it's August of 2015. We're going to do a flyby. That's going to be exciting. So you can see there's a lot of activity that's ongoing or planned or coming up here in terms of planetary exploration. And then this is heliophysics. And this is basically the study of the Sun-Earth connection. I think later this week we're going to have the launch of MMS, which is the magnetospheric multi-scale mission to understand how the solar wind connects to the magnetic field around the Earth, and how magnetic reconnection happens. An interesting one here that surprised me is way over here you see Voyager. I would have thought when I was growing up that Voyager was a planetary mission, but it's now so far out of our solar system that really it's measuring the heliopause and is really a heliophysics mission. So I think that's probably the only one that's migrated across here. That's an interesting thought. So let me show you a little bit about aeronautics, and here I'm going to give you a movie showing you what kind of exciting things we're working on. Aeronautics is seen as a huge growth potential in the coming decades, on the order of multiple trillions of dollars, especially in the Southeast Asia arena. Areas we're looking at are low carbon emissions, highly efficient air transport, low boom supersonics, the next generation air traffic control, direct flight, looking at how one integrates safety with the process of doing point-to-point flights in the in the national airspace. Phrase they use in aeronautics, it's with you when you fly. It's amazing how many different aspects of whether it's air traffic control, the aircraft itself, the runway structure, safety in the runway, and There's so much NASA content there. Has anyone seen the cowlings on some of the new GE engines, like on the 747? It's sort of serrated on the back. I think NASA had a role in that, and I think that's for noise reduction. There's so winglets. There's so many different elements where NASA has touched the aviation industry. So the last one I'll talk about is Space Technology Mission Directorate. There are 8 main areas that we're focused on, and these are the areas. You can see examples like high-power solar electric propulsion. This is so that we can move cargo, pre-position cargo to Mars and advance the human exploration. But it also has application to geosatellites, moving to what we call all-electric buses. Is anyone aware of the AEHF launch problem that happened a few years ago? Advanced extremely high-frequency communication satellite. I think there was an upper stage malfunction, and they were actually able to use the ion engines for station keeping. They were actually able to use those to boost up and into the geo slot and save the mission. So now there's a lot of idea of using almost all electric buses, basically using ion propulsion for not only station keeping within the geo belt, but also for doing the circularization at geo and so forth. Another area is space optical comm. There was an interesting mission recently where through optical comm on the LADI mission out to the moon, we were able to send data at high data rate back to Earth, and that could really revolutionize the communication trunk that goes through space that move high volumes of data. Life support, Mars, entry, descent, and landing, and in fact that applies to other planets and moons that have atmospheres like Titan, Venus, and so forth. So advanced landing systems, space robotics, lightweight space structures, not only for human habitats, but also telescopes and other kinds of large systems that need to be lightweight, deep space navigation, and space observatories for some of the advanced astrophysics missions that are going to follow James Webb. So now what I want to do is I want to walk you through a couple of the missions that we're focusing on and show you how these different directorates come together to make this possible. So for human exploration, really the ultimate horizon is Mars, but it can't be just the Human Exploration Directorate's mission. It really needs to be all of NASA's mission, and in fact, it has to be more than NASA's mission. So we need to take the rest of the world along with us to do this. So this has been direction from the president that that's our destination. The nice thing about Mars is when you look out through the planets, it's the only destination that really looks, habitable at this time. But the thing is, it's so difficult that to get there really needs us to use the commercial sector, science, the Human Exploration and Technology Directorate. And again, it's first figuring out how to work in, how to develop the tools in Earth orbit, how to exercise those tools and make sure we understand how to use them, and then finally do the mission. So let me step through this. So I'm going to start with Earth Reliant. So you've probably heard about the commercial program that NASA has been supporting over the years, commercial cargo and commercial crew. So for commercial cargo, we have 2 companies, SpaceX, that has been delivering cargo to space station, and Orbital Sciences, that's been also delivering cargo. This is a new model for supporting space station in the sense that we pay for a service, so let the commercial sector provide that service. We pay for pay on delivery, much like you might do with a package parcel delivery service. In making a market for these companies, we allow them to get their feet under them so they can start trying to capture other markets. And actually, that's been quite successful. For the first time in a long time, the U.S. has captured a major portion of the commercial satellite launch. Basically, the U.S. had lost that for at least a decade, and now SpaceX is launching commercial satellites in addition to sending cargo to the International Space Station. So that's a nice way to engage with the commercial sector, where we provide a stable market for them so that they can develop their capabilities, and then they can then use those to capture other business sectors. Recently, we also announced commercial crew, so we can start launching U.S. astronauts from U.S. soil on U.S. rockets. And we should be starting launch in 2017. There are two companies here. There's Boeing as well as SpaceX, and that's what we call the Launch America program. So we're starting to see the end of that gap that happened after the termination of shuttle. We'll start seeing launching U.S. astronauts from U.S. soil again in the near future, and that's important. So the other piece of the Earth Reliant phase is the International Space Station. It is a wonderful lab. It's got a lot of capability, but we're having some difficulty transitioning from a build and sustain mentality with station to an actual research laboratory mentality. And that's one that we got to start making that transition soon. How many people have seen space station fly overhead? We're in an engineering department here. We're at a university. Okay. It is surprising how bright and how fast that thing is moving when you on some occasions, especially when you get the sun angle right off those solar arrays. It's really it's brighter than landing lights when you're at the airport. It's impressive. So now is the time to start using space station, and it was originally sort of planned to be a science laboratory. But we're seeing more and more where the language coming out of NASA is it's also for technology, and it's also for commercialization, and it's also for Earth observation. So there's a lot of work we do in all those areas. An interesting thing that's happening is there are a lot of instruments that end up on Earth-observing satellites, and in building those instruments, we've built engineering models of those instruments to make sure that they're going to work right. Well, those engineering models can also fly. So we're starting to launch those up the station, and given its high inclination, it has a good coverage of the Earth's surface, and we're finding that fills out a lot of the data sets that we would like to have. So it's a great Earth-observing platform as well. So one thing I'd like to sort of leave as a thought for you is that station is no longer a place where you have to have a pretty mature technology and a lot of money in order to access. Station should be seen as a laboratory, like you would see a laboratory in another building, where you can go and test your technology at a low technology readiness level to the point that it could perhaps fail, so you can learn something about what causes it to fail and repeat your experiment and modify it and learn that way. And do that on a meager budget. And the reason why I think you can do that now is because over the years, test hardware and facility hardware has been launched for science and for technology. And once it's done, instead of burning it up or bringing it down, a lot of it gets adopted into what we call the national lab structure. And it's an interesting construct because it's a way. If NASA or the DoD paid for your launch to get up for station, because pretty much it's a free ride up the station, that in return for that, after you're done using your hardware, we should let other people use your hardware. So there's quite a lot of facilities up there. In fact, if you go to this site, you'll be able to find what facilities are up there and what some of their capabilities are. And if you can't, please let me know, because one of my jobs is to make station more usable. So what I'd like to see happen is that researchers with modest resources can access the national lab facilities as they would their own laboratories on Earth. So if you have a small grant, $100K, let's say, or it's a fellowship, and you'd like to be able to do some work in a microgravity environment or do some Earth observation work, you should be able to do that. Because you can borrow a lot of facilities that are already up there. So I'd like to use this to engage the broader research community through an easier two-step process that if you have an idea and you'd like to fly it, that you can get the right to fly separate from having the funding that would allow you to perhaps fly a new experiment or to access this. It's a model that's used in the Department of Defense through their DoD Space Experiment Review process, where if you have a good idea, they will give you a boarding pass, and then you can use that boarding pass to go get funding. That sort of helps to ease the process of getting on station. Or you can go and use something that's already on station. And the way we're trying to increase this awareness, and actually getting feedback from you would really help here. We're starting to write that language into research solicitations. When I first got to NASA, I said, do we tell them we do not accept proposals for station experiments? They said, no, we don't say that. I say, well, do you encourage them? They said, well, we don't say that either. So I said, well, a lot of people would think that getting on station is a very difficult and expensive process, and it no longer has to be that way. So I would encourage you to take a look. If you're writing a research proposal to NASA, or you are like a NIAC, a NASA Innovative Advanced Concepts activity, and there's something on station you'd like to use, or you're writing a NASA Space Technology Research Fellowship proposal, and there's something on station you'd like to use, I'd encourage you to propose that, because I'm working hard on the NASA side to make sure that just because you propose to do something on station, we shouldn't reject that. We should encourage it. So please be my test cases. I strongly encourage you to do so. Take a look at this site, see what's already up there, and it really has tremendous capabilities. I mean, multi-channel HD TV, all the power you might want, in-flight maintenance, a whole bunch of resources that you could use. So from the science perspective on the path to Mars, we're already on Mars. There's a number of orbiters that are there, as well as coming online. There are a number of rovers. You're probably familiar with the Curiosity rover that landed, I guess, 2.5 years ago, 2012, August 2012. But there are more systems coming online. So we're really starting to understand Mars in a very intimate way. In terms of heavy lift and crew exploration, you might recognize these. This is the Space Launch System. This is the cargo variant. This is the crew variant. We're past what we call critical design review. We're actually building the rocket now. Did anyone watch the flight of Orion in December? Anyone knew it flew? Okay, great, good. So that was a test of the guidance system, the entry system, the thermal protection, and so forth. The first stage rockets are being tested. These are the shuttle main engines. There's also larger solid rockets that are derived from the shuttle program, and the barrel sections that contain the first stage hydrogen and oxygen tank are being built right now outside of New Orleans. So this first flight should occur. First flight of the SLS. It will not have a crew on board, but it will have Orion. That should occur in 2018. And this will be the largest rocket ever launched. And there are variants of this that are going to increase from about 80 metric tons up to about 130 metric tons. So it's a lot of throw mass. But it's also interesting from not only the perspective of sending humans to Mars, it's also interesting for planetary science. Because now, instead of spending 7 years doing gravity assist at Venus and Earth in order to get to the outer planets, you can cut that duration by flying direct to the outer planets and cut that time by 2 to 3 years, which is really exciting as well. So then there's the technology. And so there's a bunch of things that you have to do once you get to Mars. You have to land heavy cargo. You have to be able to communicate back to Earth, and we're looking at laser comm from Mars. Think high-definition TV from Mars. Solar electric propulsion for moving cargo, sort of pre-positioning cargo so that you make sure that your whole base camp is set up before you actually send the humans out there. You have to have ascent vehicles. You have to have robotics, surface power systems, habitats, and so forth. And this is really where the Space Technology Mission Directorate is playing a strong role. So let me give you a little more insight into since I'm the chief technologist, I should give you some more insight on what we're doing on the technology side.
By the mid-2030s, I believe we can send humans to orbit Mars and return them safely to Earth. And a landing on Mars will follow.
So we talk about going to Mars, but we've been going to Mars since the 1960s, doing flybys. We've been doing landings. The Viking 1 and 2 landers were in the 1970s. We've been fascinated with Mars for a long time here. We've been actually landing and roving on Mars since the 1990s. with Pathfinder and Sojourner, and then Opportunity and Spirit, and now Curiosity, and then Mars 2020, which is coming in 2020. But sending humans is the next big challenge, and there's a whole bunch of challenges there: how to land all their equipment, how to survive the environment. It's extremely cold. How to send data back, power. So these are those 8 areas I was talking about. So some of the things we're working on are communications, and navigation, so laser communications. Also using natural objects like pulsars to do sort of solar system-wide navigation. There's some interesting technology there. Lightweight structures, sort of composite cryogenic tanks as fuel depots and to store the cryogens we need for rockets and so forth. Landing systems, inflatable hyads and syads, also retropropulsion landing. There's an interesting relationship with the commercial sector where NASA is buying data products from the retropropulsion work that SpaceX is doing. Also, human and robotic interactions. Some of the places where the most interesting science lies is where it's most dangerous for humans to go, so how to interact there. Radiation is something we're concerned about. It's not only what comes from the sun, at least you know the direction that's coming, but actually the galactic radiation, which is more concerning. There's recycling. So how do we scrub the CO2 out of the air, yet recover the oxygen from it? How do we extract water so that we can recycle and don't have to bring it all with us? Advanced power generation and storage is another challenge we're working on. Extracting oxygen from the Mars atmosphere. There's an experiment called MOXIE on the Mars 2020 rover, which is going to show that demonstration. So now what we're seeing is there's a number of missions that the Science Mission Directorate is sending to Mars that have technology risk reduction experiments that are important for the human mission. So those 2 missions are now starting to come together. And it makes a lot of sense because the Science Directorate knows how to navigate out in deep space. They have experience landing. They know where the water is. Water is as precious as gold, more precious than gold. We know where all those resources are. We know where you'd want to land with humans. With humans coming out there, they need to do deep subsurface access. Science would love to get better access to its samples. So it's really a synergistic mission that's starting to come together now. Another interesting combination that's happening is on our missions that enter, we've actually instrumented the heat shields with a instrument called Medley. So we're able to measure the heat loads and the burn through that's happening no burn through, but at least the ablation rates of the heat shields. And so that's another example where we're getting a better knowledge of how that technology is working so we can be more efficient in developing our future landing systems. So let me show you one about entry, descent, and landing. And this is something that was tested last year by the Space Technology Mission Directorate. And this is interesting for multiple reasons.
NASA's Low-Density Supersonic Accelerator project conducted the first shakeout flight of a new way of testing technologies that will one day be used to land heavier, more massive payloads on the surface of Mars. We used a large 34 million cubic foot scientific balloon to hoist a 7,000-pound test vehicle to an altitude of 120,000
Hawaii, so this is a good program
feet.
to get involved in.
The test vehicle was then released from the balloon, spun up for stability.
So we're above 100,000 feet here, where the atmosphere is about the same as what Mars is.
And a large solid rocket motor accelerated to over 4 times the speed of sound and an altitude of 180,000 feet, a condition very similar to the conditions it would see at Mars. Once we reached the correct speed and altitude, we despun the vehicle. And then we got a chance to test our new supersonic inflatable decelerator.
So one way to increase drag is increase surface area.
We see that inflated very uniformly.
So since you're stuck inside the capsule, how do you do that? Will you inflate or
and
you
now we're
deploy
seeing
some
previously
larger
unreleased, high-definition, high-resolution, and high-speed video taken during the test. We used the supersonic inflatable decelerator to slow us to something closer to 2.5 times the speed of sound. We use a balloon to help deploy the new supersonic parachute. The Balut is shot out the back of the vehicle at over 200 feet per second, and then we cut the balut free, and it begins to pull the parachute off the
Now
back
watch
of the
this
vehicle.
closely. Not good.
As the parachute
right?
begins to inflate, we see one of the surprising aspects of this test, which is the early onset of tears in the parachute. We see where those tears began, how they propagated, and otherwise how the parachute behaved as it began trying to inflate behind this very blunt object moving 2.5 times the speed of sound, punching a hole in the atmosphere and creating an extremely turbulent, chaotic environment for the parachute to exist in. We now have a data set that we will use to prepare for 2 more tests
So that's why we
beginning in
test.
June of 2015.
What I like to say, I worry that NASA's getting into a little bit of a culture where we have an aversion to test. Test is where you learn things. Test is where you can take it to destruction, and then you know where the edges of your technology are, and you can, as long as you can learn from that test, you can then redesign it and make it more robust, better performing. So I like to think of it as the only test that fails is one we fail to learn from, and I think that's an important thing to keep in mind. As long as you can learn from those tests, then you can come back and improve the technology. So that, if you remember Curiosity, that was 1 metric ton landed on Mars, and that's all we've been able to demonstrate so far. With this technology in the state that it was in that, well, if the chute had worked, that would land 2 metric tons. And so we're trying to get more and more mass because the human mission is going to require more mass on the surface. So let me step back to a little bit about space technology, why we invest there. Well, that's where the innovation solutions come from. If we keep using the technology we have, we really can't sort of go to a new class of NASA missions. Technology also allows us to be more affordable and reliable, and we can also create markets and spur innovation. We can transfer that technology to other sectors that can use it. In fact, mostly your smartphones, the little camera in there, that's licensed from NASA. That technology was developed for Mars rovers. And it engages the brightest minds, particularly in academia. So that's one of the reasons why the Space Technology Mission Director was brought up, is to re-engage academia in NASA's mission. So our guiding principles for engaging universities is really a broad engagement ranging from professors to graduate students to undergraduates, basically through a number of different types of programs, and to do that across a broad technology readiness level from basic research up to programs like what you just saw, a big tech demo kind of work. And with an emphasis of forming close partnerships with STMD and the NASA centers. So we have several programs where we do this. There are space technology research grants and fellowships, as well as I wanted to point out here that right now we have open an early career university faculty. So you've probably heard of such programs they have in the DoD. Well, we also have one in NASA. I think the proposals are due in May, so I encourage you for the early career faculty to propose. We also have the NSTRF, which is the fellowship program for graduate students. This will give you sort of a snapshot of the different number of awards and the number of university-led projects. And it really is climbing through sort of the different aspects of STMD, from the fellowships through the NASA Innovative Advanced Concepts, through game-changing technologies, small spacecraft, flight opportunities, different modes. You can see there's a lot of university engagement, but we could sure use a lot more. On the technology research grants, we have the fellowships. Here's a bunch of mugs of the various students that have held those fellowships. The proposals are due in the December timeframe, so please think about proposing. It's a nice fellowship, which has each year of the fellowship, there's an internship at a different NASA center. It also has travel money that comes with it. That's always a precious commodity. The Early Career Faculty Awards, that's open right now. Early Stage Innovation, to think about sort of the seed corn, develop the seed corn for future advanced technologies. So I'd like to take you a little different direction. Say we've focused a lot on Mars. I want to tell you what else we're doing. I mean, everything we do seems to be related to some fundamental questions. Where did we come from? Where are we going? And are we alone? And that are we alone piece is really the search for life. So Mars is Mars is sort of about the migration of life. The human exploration to Mars is about the migration of life off the planet, permanently become an interplanetary species. But there's also looking for life elsewhere in the universe. And there's some interesting results that are happening. And they aren't necessarily where you might expect them. So obviously there's, at Mars with our rovers, we're looking for follow the water, find the building blocks for the chemistry for life, and then eventually find life. And in fact, we're finding there's water everywhere. You dig in a lot of places, there's water, there's frost very close to the surface. There are actually ice caps that are high purity water pretty much sitting right on the surface. So that's great. There's also big methane plumes we're finding coming from underground, and we're wondering what's causing that methane. It could be life. But another place we're finding interesting possibilities are on some of the moons. So this, I think, is Europa. That's a moon of Jupiter's. This is Enceladus. It's a moon of Saturn. So the Cassini spacecraft is currently at Saturn, and we've seen these geysers. This is ice. This surface is ice. It has a ocean underneath it. There's more water on the moon of Enceladus than there is on the entire planet Earth. It's pretty amazing to think about. A moon that's smaller than our moon has more water than our Earth. And that's because it's got a 50-kilometer deep ocean, and that's all it is. It's a warm ocean with a solid surface of ice, but it's heated somehow. It's around Saturn, and we think we're probably pretty sure that it's the gravitational tug from Saturn is stretching that planet and heating it up. And so that gives you a liquid ocean. So recently, we flew Cassini through these plumes. And they're rich in, what's the right word? Organic compounds. We don't have instruments to detect life, but the chemistry for life is there. We just can't measure if it's actually there. And in fact, when you look at some of these splits in the ice, they're off color. There's something that's staining those cracks. So that's very interesting as well. So in fact, in searching for life elsewhere in the solar system, we might find it at Mars, but we might find it within these sort of water worlds, which are moons around other planets. There's also the search for planets around other stars, exoplanets. So here's a scale to think about when thinking about exoplanets. What's the mass in Earth masses? So here's 1. There's Earth. What's its distance from its parent star? There's 1 AU, so there's Earth. Here are the various planets in our solar system. These are the other planets we're finding around other stars. I mean, it's with the Kepler mission. Anyone heard of the Kepler mission? I mean, we're finding we're hundreds of planets. If you get the little app on your phone, that app is going off several times a day as we find more and more planets. And the better our instruments get, the smaller the planets are, and the closer into their. Actually, Kepler captures a lot of these planets that are close in because it works through occultation. And we're starting to find planets that are in the Goldilocks zone, basically the region where water might exist in liquid form, much like basically analogs to Earth. So here's sort of a histogram. This is changing every day. We do find the large planets. They're easier to detect, but actually they're in the minority. The most common planets we're seeing, but that doesn't mean it's the most common. It's just of the ones we can detect are more of these Neptune-sized planets. But we're finding a lot of supersized Earths down to Earth-sized planets. And, again, this is leading to the point of, at some point, will we find that pale blue dot out there that is Earth, and we can characterize it. So the next emerging field that's happening is as we detect the existence of these planets, can we actually capture starlight that's been refracted through an atmosphere, if it exists, look at the spectrum that has been added by that atmosphere, and see what kind of molecules might be in that atmosphere. Does it have water? Does it have ozone? Does it have methane? Does it have carbon dioxide? You can tell a lot from the spectrum of starlight that is refracted through the atmosphere of these planets. So when you think about that we know of the existence of almost 2,000 planets that are outside of our solar system, and then you look at the field of view of Kepler, which is about 1 degree, No, I think it's actually less than 1 degree on the sky, and then you imagine the whole sky. What you figure out is that there's probably 1 billion Earth-like planets in our galaxy alone. And the question is, do they, Earth-like planets in terms of size, liquid water, potential for liquid water, and then you start thinking, is the population large enough that we could actually start thinking about life on those planets? And it becomes very interesting. So I'd like to leave you with that thought about that NASA's mission is mostly about the migration of life off the planet as well as the search for life elsewhere in the universe, and encourage you to get involved in that mission. Thank you. Be happy to take questions.
Absolutely. And if you have a question, we would encourage you to use the microphone that is over there.
Hello.
Sure.
Hi, Dr. Miller. So my question is, in the next 1 to 2 decades, what do you think are the largest, most significant technological roadblocks that NASA and the aerospace industry faces as a whole?
Well, that's a good question. What are the largest technological roadblocks? Well, for NASA's missions, I think one of the difficulty when you look at the human exploration, getting down to the surface of Mars, I think when you look at the plans that exist now, we're talking about 40 metric tons on the surface. In order to, basically that consists of the surface equipment, the habitats, the ascent vehicle to get back off Mars, return home. So NASA sees the early exploration of human exploration of Mars as a round trip exploration. So, we've been able to land 1 metric ton. We're working on technology that can land 2 metric tons, but we need 40 metric tons. And so, how do we solve that problem? Do we keep shooting for 40 metric ton lander, or do we start thinking about 8 5 metric ton landers? How do we start trying to solve that problem? I think we have to think differently than perhaps how we thought about landing on the moon, in terms of how we deploy equipment and people onto the surface and get them back off. I think another area which for that mission, which probably hasn't received as much attention as it's worth, is in situ resource utilization. When we travel places, we don't bring all our water and all our food with us unless you're going camping. But we bring certain essentials, and then we buy or extract what we need, and I think that's a real game changer. When you think about exploration, human exploration to Mars, I think that it's really a logistics problem. Where are you going to go? Where are you going to fill up the gas tank in your car? Where are you going to get your drinking water? Where are you going to get your food? You have to think that all out, because I think how you do that really drives what it's going to cost and whether it's sustainable. And the key is, because the way it's so difficult to explore, to send humans to Mars, that NASA feels that it's not only an exploration mission, it's also a pioneering mission. So every time we go, we should leave something behind. So every successive mission is easier. So I think ISRU is a big piece of that. Yeah.
Thank you.
Sure.
Hello, Dr. Miller. I'm sure you've heard of Mars One. I don't know if does NASA get involved with companies like that. I know they want to land a one-way trip of humans to Mars in the 2020s. Would NASA get involved with them or help them out?
We think the excitement about Mars worldwide is wonderful. We like to fan the flames on everyone that's interested in Mars, and it's. I think that excitement is very interesting. If people want our help to try to think about different aspects of the mission, we're happy to help. We're not trying to pick winners, and say your idea is good and your idea is not. We're happy to help where we can. So I think all those. I think just the excitement about Mars worldwide, I think, is fantastic. So, and that's one example. Yeah.
Thank you.
Sure.
Hi, Dr. Miller. My question is, based on your experience in the CubeSat launch initiative, what do you see the future holding for CubeSats, not only in an academic environment, but also in industry?
So I like to think broader than just CubeSats. I think sort of the small sat or the microsat, however you want to categorize it. I see a lot of possibilities in the future. I think there's an educational promise there that we've already seen. I think that's great. It's sort of like sounding rockets were as a part of an education, a few decades ago, where you actually got to think about the research you wanted to do, build your experiment, launch it. If it didn't work the first time, you can fix it and try again. And I think CubeSats give you a great opportunity to do that. We're starting to see that migrate into more operational systems, scientifically interesting experiments, or which might actually and hopefully grow into operational systems that we depend on. And so I see a nice sort of seamless migration from education through technology, maturation and development through sort of first-time prototypes of observation systems or scientific systems to actual things we depend on for every day. I think the idea of being able to build small pieces of a larger architecture is a real enabler in this field. So if you build one big satellite, it's so expensive you probably can't afford too many. And when you can put smaller sensors on multiple satellites and build a cluster or a constellation, now you get an element of spatial diversity, which gives you a more rapid coverage, return rate over different places. There's a whole sort of architectural domain that allows that to be reachable in an affordable way. So I think, I don't think we've only scratched the surface of what small satellites can do. Yeah.
Thank you.
Sure. While you're waiting for another question, I'll ask myself a question. Okay, sure. So I was asking an astronaut what was sort of tell me something you don't know that I don't know about space flight, and I've been in this arena for a long time, never flown, but got a very interesting answer. So on the ground, we have our frame of reference. This way is up, right? That's forward. So now put yourself on the shuttle, and you're doing an EVA, and all the expensive equipment is in the payload bay of the shuttle. So your legs are actually very powerful in space. They're more powerful than you need. Because on the ground you have to hold your weight, you run, you walk, you have to lift things. But actually they're a little too powerful on orbit, so what they do when they move around the payload bay of the shuttle is you like to move along the edge, sort of the hinge line between the door and the payload bay, and that's where they have the handholds, the rails, and you sort of do it like you're doing a handstand. So you're walking along with your legs away from the shuttle so you don't kick something very expensive. So you're doing that, and typically for thermal reasons, the shuttle would fly with payload bays facing the Earth. And they said, you're doing this, you're moving down the length of the payload bay, thinking you're doing the world's best handstand. And then within a fraction of a second, you feel like you're hanging from the shuttle, 300 miles up in space, and you freeze. And then your mind flips back again, and you're doing a handstand, and you feel comfortable. Then it flips again, and then you freeze. And it's your mind, I guess, searching for a frame of reference. And without the gravity vector there, telling you which way is up, your mind is searching. And they say, it's... Of course, the astronaut telling me the story said it never happened to me. But it happens to everyone else. But they said, it's quite disconcerting when it happens. So that's I hadn't thought about that. But have I stalled not enough for another question? I'll add another element to that. I'm 1 minute over. This will be a short story. So another one is this astronaut had been up on space station for 6 months. I asked the same question, and they said, well, there's 3 things you want to do when you return to Earth. One is hug your family. Second one is have your favorite dinner. And the third one is take a shower. You might want to do that in a different order. But they said when taking a shower, you start at the top, head to the bottom. And so, going to shampoo your hair. And you close your eyes so that the soap doesn't get in your eyes. You fall over. Because your inner balance is gone. It hasn't been useful to you for 6 months. Your brain has learned to ignore anything that comes from your inner ear. And basically all your orientation is done visually or contact, touch. But so when you're back on Earth and you shut your eyes, you just fall over. And so he said you had to sit in the shower, had to sit on the floor of the shower for like a week doing that, leaning up against the wall. Then he could sit on his, sort of on his knees. And it took him about 2 weeks before that whole system came back, which was kind of interesting. But I'll stop there.
All right.
Thanks.
Well, thank you very much. Dr. Miller, we have a little frame of that will remind you of your visit.
Thank you very much.
Risking you live through this ice storm to come and talk to us. So we really appreciate it. We realize it's going to be very hard for you to carry it with you, so we'll take it back.
Oh, okay.
And,
hey.
And we'll ship it to you.
Well, thank you.
So please join me in thanking Dr. Miller again. We'll be more than happy to, I'm sure we'll be more than happy to tell you more stories of astronauts.
Or graduate school stories about Professor Chung.
If you want to know everything about
I brought
Suzhou,
pictures.
please do.
So
thank you again.
Thank you.